For those who are new, this series uses www.falstad.com for circuit simulations. Hello everyone. In this video, we will explore step by step how a capacitor works using Falstad simulation. Capacitors are used in almost all electronic devices. For example, in phones for stabilizing energy, in audio systems for filtering sound, and in LED lamps for storing energy. The main function of a capacitor is to temporarily store energy and release it when needed. In this video, we will watch its charging and discharging process step by step. In our circuit, we have a battery V equals 5 volts, a capacitor C equals 200 microfarads, and a resistor R equals 100 ohms. Tau, or the time constant, shows how fast the capacitor charges and discharges. Tau calculation. Tau equals or time C equals 100 times 0.0002 equals 0.02 seconds equals 20 milliseconds. For this circuit, the value of each horizontal branch gives a tau of 20 milliseconds. Practical charging. 1 tau, approximately 63% charged. 2 tau, approximately 86% charged. 3 tau, approximately 95% charged. 4 tau, approximately 98% charged. 5 tau, almost fully charged, approximately 99%. After 5 tau, we can see that the capacitor is about 99% charged. So, for this circuit, the capacitor becomes almost fully charged, and 5 times tau is equal to 5 times 20 milliseconds equals 100 milliseconds equals 0.1 second. As you can see from the formula, the capacitor does not charge at a constant linear rate. If we reset this circuit, we can see that after a while, the current flow becomes steady. As the capacitor starts charging, the voltage across its terminals increases. Because of this, the current through the resistor gradually decreases. In an ideal capacitor, which we use in this and other simulations but does not exist in real life, when it is fully charged, the voltage reaches its maximum and the current becomes nearly zero. The time-dependent variations of voltage and current can be determined using appropriate equations. The voltage is shown in green. The voltage across the capacitor rises as it charges. V of t equals V times 1 minus e to the negative t over tau. Simplifying the formula gives us this result. Voltage over time. Time 20 milliseconds. Voltage 3.16 volts. Time 40 milliseconds. Voltage 4.32 volts. Voltage 4.75 volts. Time 80 milliseconds. Voltage 4.91 volts. Time 100 milliseconds. Voltage 4.97 volts. By 100 milliseconds, the capacitor is nearly fully charged. Current shown in yellow. The current changes according to the formula. I of t equals I naught times e to the negative t over tau. Simplifying the formula gives us this result. Current over time. Time 20 milliseconds. Current 18.4 milliamperes. Time 40 milliseconds. Current 6.8 milliamperes. Time 60 milliseconds. Current 2.5 milliamperes. Time 80 milliseconds. Current 0.9 milliamperes. Time 100 milliseconds. Current 0.3 milliamperes. In Falstad, you can see the current dropping quickly, almost reaching zero by 100 milliseconds. When we change position the switch, the capacitor discharges. During discharge, both current and voltage decrease exponentially. After 1 tau, 20 ms, about 37% remains. After 5 tau, 100 ms, the capacitor is almost fully discharged. Their discharging formula for current and voltage. Negative current in Falstad means the current flows in the opposite direction. Voltage does not become negative because it measures the potential difference between 2 points. Current is like water flow, direction can change. Voltage is like water height, always positive. Summary. Tau equals time constant. It determines how fast the capacitor charges and discharges. Charging. Current decreases exponentially, voltage rises. Almost full after 5 tau. Discharging. Current and voltage decrease exponentially. Almost zero after 5 tau. That's all. You can also change easily the values of the capacitor and resistor log video shown to calculate and challenge yourself. And if you found this video helpful, don't forget to like and subscribe. See you next time.